Number 36, the crazy Niagara Falls question. Well, in this problem, they want to know power, and they tell us that we have 1.2 times 10 to the 6 kilograms per second of water, and it falls 50 meters. How much power is generated by the waterfall? The weird thing for this problem is the units that they give you. They give you mass per second, which you're just not accustomed to seeing it that way, but you can kind of slide that T anywhere you really like. So mass per second, a distance of 50 meters, and by the way, what makes the water fall? I think it's gravity, and so you can put G in there. So that mass per second times G times the distance, and you just multiply, and you get an answer that is 10 to the 8th power in watts. So it's going to be a ginormous amount of power. Well, it's Niagara Falls. It's going to be. And that takes us to number 52. 52 is a bit of a doozy, but you can handle it. And the big idea in this one is that the conservation energy is going to make the ball roll down the ramp, and it'll give you a velocity. And then you can use projectile motion to figure out where it lands. But actually, I said that backwards in this problem because they tell you where it lands, and you have to use projectile motion backwards to find out how fast it was going. And once you know how fast it was going, you can figure out how high up it was. Okay, here we go. They tell us that we have this ramp, and then the ball falls after the ramp and goes outward and strikes here. So the mass of the marble in the problem is totally irrelevant. Just forget about that mass. Yeah, I didn't do stunt. That was just my hand catching. We know that it went sideways 1 meter. We know it fell 1.25 meters vertically. So what you have to do there is they want to know a number of things, and I don't care what order you do this in. I'm going to tell you what order to do it in. Find the velocity of that marble first. So what do you need to do? You need to take that 1.25 meters and use it with that falling equation, where delta y equals 1/2 a t squared, 1/2 g t squared. Then they'll tell you that after falling 1.25 meters, it will take a certain amount of time. With that time, and I'm thinking it's roughly in the neighborhood of half a second, with that half of a second of fall, you're going to take that here and say delta x equals v times t. So 1 meter equals v times half of a second. You're going to divide by half a second. 1 divided by half is like 2. So it's going to be something like 2 meters per second when it leaves the ramp. Well, now, it's just like the skiers. We got some potential energy up here. It changes into kinetic here. So we can use this idea right here to figure out how high the ramp is. We know the velocity this time. Vi is 0. Find the height. So you plug in that theoretical 2 meters per second here, solve for the height. And in reality, that's the big idea in the question. They want to know what's the overall height that it falls. Well, you take your answer and you add the 1.25 meters to it, and that gives you the answer out of the book. What does it say out of the book there? 1.45 meters. And then what height above the ground does the ball start? So 1.45 meters. What's the speed of the ball when it leaves the track? That was the 2 meters, like roughly the estimated 2 meters per second we found. And then what's the speed of the ball when it hits the ground? You could just then continue extrapolating that velocity as it falls, but I really don't care about number C. That's the review. Good luck.